Okay, everyone. How are you? I haven't seen you in a week. Sorry about that. So, a few things. I apologize about Friday. That meeting was with the West Coast, and it was really supposed to last until 2:30 or so, but they ran late, and I couldn't get out of it. So I had that feeling when I sent you that email 2:15 that it wasn't going to happen, so it didn't. We ended up at like 5 p.m. So, and Patrick was in that meeting too. So sorry about that. So this week I was in at Daytona State College for a seminar Monday. That's why we didn't have class. And they recorded my seminar, so maybe I'll post it at some point if they give me the link, if you're interested. So this week we have this class, and Friday as scheduled. I'm not going to start any new topic, or well, yeah, new topics, but not new chapters. We'll start maneuvers after the spring break. So today I'm going to finish up on Euler angles and how they are used for angular velocity representation, so that we all know Euler angles once and for all, and we are on the same page. You may have received my email about question 7. I really realized that the vast majority got it right, but still, I gave 5 points to everybody across the board, just because some have been confused by that, and I consider the topic closed from my point of view. Most of you got it right, so there is a percentage that was confused. That is my way of addressing the issue. If you have any other concerns, you can come see me. We do have a new classroom for tests, which is the biggest one in the new physics building. I looked at the map, it's huge. So you really are going to sit and have no one on your sides. It's for 300 people. And they are real desks, as far as I know. I have to check it out, but I've seen some pictures. So finally, we can be comfortable. Someone asked me about the midterm survey. I'll send it right after the spring break, and I'll give you a week to return that thing to the TAs. I don't need to see your individual ones. It's a Word file with a few questions. You just send everything to Patrick and Thomas, and they just run the statistics. You just do an average, and we'll discuss them in class if there are any issues. What else? Well, tonight, I don't think it's going to happen, but SpaceX is supposed to launch something at 6:45. But I was actually at Kennedy yesterday, and they may cancel because the weather is not that great. So I don't know, are we able to see launches from here? Sometimes we can, right? Yes. So, well, check it out. I don't think, even if they launch, we probably won't be able to see it, but they're doing amazing things at Kennedy, by the way. It's really exciting. Okay, so let's, do you have any questions, comments, concerns before we start? Have you all solved uncollected homework 3? Some of you. Really, believe me, there is nothing better than doing it yourself on paper and translating into MATLAB to understand the relatively simple procedure to go from a set of coordinates, Cartesian, to orbital elements and vice versa. That is the best way to learn it. And believe me, if you develop your own function, even though I posted mine, it will help you. So if you're behind, try to catch up with the homeworks that I give you that are not collected, because they have a reason to exist. Okay, let's look at Euler angles and how they are also used for the full representation of three-dimensional angular velocity. And I'm going to stick with the sequence we have used for orbital parameters, but really what I'm doing, you can generalize it to any sequence. Maybe I'll just give you another uncollected homework where you do it for a sequence 3, 2, 1. The procedure is the same. You just change one of the axes. Well, in that case, 2 axes. But let's repeat a few of the things, the sketches that we have seen. So with the 3, 1, 3 sequence, before I even start talking about angular velocity, we said I'm going from the original basis that I called x, y, z. I rotate about this axis, and let me just reuse the same names for the angles. But again, these, you can generalize it and start calling those angles alpha 1, 2, and 3. I don't care. I'll call them here ran, inclination, and argument of perigee, just because that's what we have done last time. But this can be called anything you want. So with this rotation, the z prime and the z are the same. You move these 2 axes in the xy plane. and you get a y bar prime, I'm sorry, this is x, of course, x bar prime and y bar hat, not bar, y hat prime, okay? Now, one thing we could imagine is that, as we commented last time, that the initial orientation x, y, and z without any prime or second or third, it's how your object was oriented at some initial time. And then you go through the sequence of rotations to represent how it's oriented now, right? So in other words, I could think of the following. I can imagine that this basis, x, y, and z without any superscripts, is the basis fixed in some coordinate, in some reference frame A. I can do that. While the new basis, this one, with the primes, let's just call that, I don't want to use B for a reason, C. So we can imagine that we're looking at some physical object, a rigid body, a reference frame, that it's rotating and going into the C configuration, right? So what can I say, which we have seen at the beginning when we have refreshed dynamics? This is a single axis rotation. I can tell something about the rotational state of C with respect to A. The angular velocity of C with respect to A is what? As a vector, which is quite simply that omega dot z, or z prime, it doesn't matter, right? There's a few things I've given you when we refreshed dynamics at the beginning, such as some properties of the angular velocity, the transport theorem that we don't demonstrate because they come from general dynamics, but we should know. So that is, you know, single axis rotation. And then what am I going to do from this? I'm going to do another single axis rotation, right? So the second rotation is the following. I'm going to try to avoid rewriting names of too many axes here. Only the ones I really care about for each rotation. X prime is here, y prime, z prime. So we have this second rotation of an angle I about the new x-axis, which leads me to z second. So I go here, and this y prime goes up. It's leaving the xy plane, of course, right? By the same angle I, and goes to y second. Okay? Make sense? So the only axis that remains fixed, of course, is this one. At each rotation, I have one axis that remains fixed. It doesn't change. And the same reasoning goes here. If I went from this basis with the prime, which I have called C, was fixed in some reference frame C. Now this is going to be fixed in some other reference frame D, for example. Well, I know that D moves with this angular velocity with respect to C, given by, and you're going to forgive me if I do I dot, like that. I hope you understand it. Two dots. Two vertical dots. About x prime, or x second. It's the same thing. And so I have this specific single axis rotation addressed. And then the last one, let me fit it in here, is going to be, let's see. Yeah, we can try. Which axis am I going to use? The z, right? The z second is z third as well. And I'm rotating here with a little omega angle, is the last one, that is going to move my x second into some, so let's see. I don't really need this one. Okay, so this is x second, this is y second. And in the plane that contains the two, I'm going to move them. So this is lifting up, going somewhere else, to x third by the same angle. And this is also going to lift up somewhere by the same angle, and you have y third. So you grab this basis with the second and rotate it about the z-axis. And so here I'm going from D, which was my basis fixed, well, with the second superscript, so say that this is fixed in D. And say that the final one is, let's call it B, which is the final one. I don't have any more rotations. And so the angular velocity of B with respect to D, it's another single axis rotation, is little omega dot z second or z third, it doesn't matter. It's the same thing. Is that clear enough? What is going on?
Can you go over the second diagram?
Second one?
Yeah. So
Okay, so this is where I left off, and I am moving here, and I have x prime, y prime, y prime. I rotate about x prime. It doesn't change. It doesn't change, of course, because that's the axis of rotation. Z prime goes somewhere here, and y prime leaves the xy plane and goes up. So each single rotation is about one of the coordinate axes, an intermediate one, but that's what it is. Are these individual rotations okay? So again, grab an object, rotate about an axis, you look at the new direction of the x-axis, rotate about that one, look at the new direction of the z-axis, last rotation. Z, x, z. That's the sequence 313. And I know I can write the single rotations like that in terms of angular velocity. What is one property I know about angular velocity? If I have multiple frames involved, the chain rule, right? Remember? So, if I want now the angular velocity of B, which is my actual final object I'm looking at, I want to write how it's moving with respect to the original reference, the A one. Well, I can break it down into what? The angular velocity of B with respect to D, angular velocity of D with respect to C, angular velocity of C with respect to A. Again, we have not demonstrated this, but you should know this from dynamics. Remember the chain rule. So you go from B, D, D, C, C, A. And so you're going from A to B. So this is a valid relationship. Now the problem is that all these, as you can see, these intermediate rotations are about different axes that belong to different coordinate systems, of course. But this is perfectly fine. These are all vectors. I can write these. There is no federal law that prohibits from doing this. I can sum together vectors that are expressed in different bases because they are vectors. You can always write it. It's not forbidden. Then a different story is if you need to project on the same basis, which we will need to do. So that is a perfectly fine expression right there. Second or third, again, is the same thing, okay? Make sense? So, let me do this, and I'll tell you why after I do it. Usually, of course, we don't stop here. We don't like the fact that, well, this is a basis in the prime coordinate system, and this is in the second. So we're mixing bases here. Usually what we do is we express this angular velocity in the same basis, of course, and it's the last one. It's the B coordinate system. Imagine that this is a physical object, that it's moving in space, rotating, and it's at time zero, even though that is not true, but we imagine that at time zero is oriented with the axis of our A coordinate system, which is this room. X is that way, Y is that way, Z is that way, and it's oriented at some weird orientation. And I'm trying to represent that by, as I said, the rotation about the Z-axis, intermediate X-axis, new Z-axis, to get to where it is. And those are the three angles, the three other angles. But I also want to express how fast it's changing orientation. And that's what I'm doing here with the angular velocity. In reality, what happens is, this is a spacecraft or an aircraft or anything that has, for example, a gyroscope. I'm sure many of you have heard of gyroscopes. Devices that measure angular rates. These things are attached to the object. They're not sitting on the floor. They are moving with the object, of course.
Okay, so what happens in real life is that the gyroscopes give you measurements of the angular velocity vector projected in the body frame, x third, y third, z third.
is that the angular velocity is something you can measure, but you can measure it in the basis fixed in B, which is my final object, right? My final orientation, my real orientation. Does it make sense? So in other words, we need to write this where all these vectors are transformed into the last basis, the one with the third, all over the place. And well, how do we do that? Well, it's quite simple. Let's rewrite the expressions that we have found last time. We know all these relationships, right? I'm not going to explicitly write the matrices. I don't need to. Okay, this gets me from x, y, z to the prime. Then I go from the prime to the second. And that is R1I. Okay, and the last one is this one. Okay. So what do I need to do there? I need to transform everything that doesn't have the third here. By the way, this already has the third. So the last one, it's fine. I need to convert these two guys into the basis, project them into the basis with the third as superscript. So how do we do that? Well, it's right here, right? I can say that x prime, y prime, z prime is what? Is R1 inverse of I. So it's the inverse of that matrix, which we have expressed last time, probably. Okay. Multiplying the basis with the second. What about this one? I can invert it as well. And it's the same, R3 to the minus 1 inverse, actually I should say, that is multiplying the basis, which is in B. So I do have a way to go from this to that, which is, do you need this in between here? Can I erase this? Okay. So what do I have? I have that x prime, y prime, and z prime are equal to R1 inverse of I, R3 inverse of little omega that multiplies the third basis. Does this make sense to everybody? We've done it last time, I believe, something like that. So now I do know how these guys project into the basis that is fixed to B. What did we say last time? That basically you look at these two matrices. This gives you a 3 by 3 matrix, of course, whatever goes there. And the first row here gives you how x prime projects into this new basis. The second one, of course, gives you how y prime projects. And that's all you need to use. Because I don't see a z, I'm sorry, actually I need x prime and z prime. I don't need the y prime, right? I don't have it here anywhere. So these, you can do it by hands, or you can do it in MATLAB, as I'll show you. How many have used the symbolic toolbox in MATLAB before? A few people. Okay, so I'll show you that in a second. Yes?
Can you repeat one more time what that first row represents?
Yes. So we agree that here we have the basis with the prime that is equal to a 3 by 3 matrix, because the R1 and R3 are both 3 by 3 matrices. If I invert them, they're all still 3 by 3 matrices. I multiply them together, they're still a 3 by 3 matrix. So I don't know how they look like inside, but it's a 3 by 3 matrix, right? And so each row is multiplying the column of these bases, right? And so this number here multiplies x, this is y, this is z, and basically it's telling you how this little vector is projected into the x third, y third, z third bases, right? And the same for y and the same for z. People usually call these rotation matrices, but they're really just transformation matrices. Just tell you how this basis transforms into this one and vice versa if you want. There's nothing that it's really rotating here. I'm not taking an object and rotating it by doing this multiplication here. It's just projecting these vectors into these new vectors. Any other questions? We have time. So if you have any concerns about this procedure, you should tell me now. So up to this point, you can redo everything, completely erasing this sequence and doing something else. You can do 3, 2, 1. What you have to do is start from sketch number 1. It will be this one. It doesn't change. But then the second rotation is going to happen about this axis. So you will have some kind of R2 matrix instead of R1. And the last rotation is going to be about whatever is the last x-axis that you get. But the idea is the same. Do it one at a time, then assemble them together. Okay? No questions. Now, so I'll show you how we do it in MATLAB, but let me give you the result. If you do that, look at R1, R3, invert them, multiply them, do the transformation. So do all these steps that I will show you in symbolic MATLAB because I don't want to do it by hands. This is what you get. You get that basically the omega b with respect to a expressed in the basis in B will look like this. A matrix. Let's see. I have sine of little omega, sine of E, then cosine of little omega, 0, 0, 1, 0, cosine of E, of I, I'm sorry, not E, cosine of little omega, sine of I, minus sine of omega, that multiplies the time derivatives of those angles, of the other angles. So this is just reorganizing what you will get from, again, extracting first and last row of this matrix here, substituting where you see x prime and z prime, so that everything is expressed in the same basis, and reorganizing things so that you collect the time derivatives of the vectors here, and this will look like a matrix. Again, I'll open MATLAB and this will be a little clearer probably, but you should be comfortable multiplying a 3 by 3 matrix times a column vector.
Okay, so this is the final expression we find given the angular velocity of B with respect to A, expressed as a matrix multiplying the vector of the time derivatives of the ordered angles, and of course this will give you a column vector when you do the multiplication here, and each of the components is a projection in the x third, y third, z third basis. So what it actually happens in real life is that this quantity, which is again a vector of 3 values, is measurable on board an aircraft or spacecraft with gyroscopes. So when you invert this matrix here, you have an expression for omega dot, I dot, and little omega dot that you can integrate in time with the measurements being the angular velocity measured on board the vehicle itself. So by making this matrix not invertible when the inclination second angle is 0 for the 313 rotation, that means that you don't have an expression that you can numerically integrate to give you the time evolution of the other angles. Numerically, analytically is not usually feasible, but numerically you could be able to integrate these given initial conditions if you have omega. measure on board. But again, if this matrix cannot be inverted, that is not possible, and that's another reason for avoiding singularities.
We'll do it in MATLAB. Any questions up to this point? So we'll stop there, and we'll look at the rest in MATLAB. Yes? No, you have to invert that matrix. So the actual inversion of a matrix, you compute its determinant, and then you go, the procedure to invert. If you want to do it by hands, which no one nowadays does probably, but we should know how to do it. There is a determinant involved that it's dividing everything, and I will stress on that because remember that this kind of sequence, we said if the second rotation goes to 0 or pi, the first rotation and the last rotation, they happen about the same axis, right? Because you're not doing anything here. So if you're rotating about the z-axis, then you do nothing about the x-axis, nothing is changing. And then you go back to the third axis, is the same one. So the big omega and little omega are about the same axis. And that we called it a singularity just because you don't want infinite combinations of big omega and little omega, right, to represent your orientation. Mathematically speaking, we'll see that the determinant of, when you try to invert that matrix, the determinant actually goes to 0. So there is also a mathematical implication for not using a sequence like this when you approach the second rotation to be 0 or pi. And the same happens for a sequence like this, which I call asymmetric. This is symmetric just because I see the 3 and the 3 here. So everything that has first and last numbers that is the same has the singularity in the middle when the angle is 0 or pi. While in this case, maybe we'll sketch it. Actually, let's do it. That happens when the second rotation is not 0 or pi, it's 90 degrees. So, say that I'm doing 3, 2, 1. What does that mean? That I start again from my initial basis. And first rotation is the same. I can still call it capital omega, it doesn't matter. So I go to x prime and y prime as before, right? Now, the second rotation is about an axis number 2, means y, x, y, z. So my current axis number 2 is this one, right? And let's keep using the same letters here. Let's call this the I angle. Again, it can be alpha 1, alpha 2, alpha 3, I don't care. Where is this z going? If I have I equals 90 degrees, where is z going? And by the way, z prime is here. So where the z second is going to be is where the x prime is, right? So this guy is going to point right down. This is terrible now. Let me move it so that it doesn't look exactly below z. Something like this. So that this is x prime, right? So 90 degrees is going to lead z second exactly where x prime is. So it's going to end up here. And x prime is going to become x second, and is pointing like minus z, right? It's right below z. Do we see that? And so since it's a 3, 2, 1, the last rotation has to be about an axis with an x. My current x is this one. So my last rotation is going to be, which was little omega, on an axis parallel to the first one. Every time something like that happens, you have what we call a singularity. In other words, you can find infinite combinations of these two angles, say that the addition of the two, that give you the same physical orientation of the object. Do we see that? If you rotate 10 degrees this way, and then you go 90 degrees, and then you go another 10 here, it's equivalent to doing 20, 90, 20, 30, 90, 30. I don't want to be free to choose any possible combinations for these two, because it's not a unique way to represent something. Again, if you have a point in space and you tell me that x, y, z are 1, 2, and 3, but also 5, 6, and 7 at a certain time, it's not a way to measure things. It's either 1, 2, 3 or 5, 6, and 7. It's not univocal anymore, right? Yes?
Can you do the 3, 2, 1 again? I think I missed.
Yeah. Do you want me to erase and redo it from sketch?
Well, willing to.
Yeah. No, this is important. Well, again, these are the things that you guys should slowly redo by yourself on pieces of paper, because there is no other way to prove it to yourself, trying to visualize these things several times alone. So this is x, y, and z. And I'm kind of afraid of using different colors just because not always they come out, the right way, but I can try. So say that, how was blue on video? I don't know, I'll try. So this is my first rotation, right? And I go here, and I go here. And this is my x prime and y prime, and they're still in the xy plane, right? I just rotate it in the same plane. So this angle is big omega as well, and this is big omega as well. And then, what do we want to do? Red. Then it's a 3, 2, 1, so I've used this one, done. Then I have to rotate about axis 2. The current 2 is y prime. And so this is my second rotation. And I said, let's look at the case when this is actually a specific number, which is 90 degrees. If that is 90 degrees, this guy is going to be, since x prime and z are at 90 degrees. Red, yeah, no, that is terrible. How about, I don't know, green? I have a limited selection here. No, green on green, that's terrible. Sorry. Bad idea. Yellow, I have yellow, yes. I like this. Is blue okay?
Yeah, blue's fine.
Okay. So do we see that z is going down here, right? Oh, look at that! I can do parallel axis now. That's great. So that was z. Z and z prime are the same, of course, and now this is going to be z second down here, and that's fine. So I've taken care of the second rotation. The last x is going down, right? X is going down, and since it's 90 degrees, the x, what is this? X second, right? Is going to be exactly parallel with the original z, right? And so my last rotation, purple, you can try, is going to be, it's not bad, right? It's going to be this one, little omega, about this same axis. And so if you imagine the following sequence, we can come up with examples. The big omega is 10 degrees. We said the I is 90 degrees. And the little omega, now this big omega was that way, little omega has to go this other way, right? Opposite. So if I do little omega equal to 10 degrees, this is canceling out the original rotation. And so, but this sequence lead my object. So again, imagine that you have grabbed an object and you've done this, then 90 degrees, and then the final rotation the other way. Don't I get the same physical orientation of the object if I do 20, again 90, and 20 on the last one? So I can keep going with these two as long as they are the same, and there is no unique values for them. And again, that is not a good idea. If you're trying to locate the state of a system, it doesn't matter if it's a point in space or the orientation of an object, like in this case, you want one position corresponding to a set of parameters, just one, not multiple ones. Otherwise, it gets, your representation it becomes meaningless, right? Yes.
So that would be fine if little omega was like different from big omega.
Oh, if they're different, it's the same. That's a good question. So if it's say that it's 30 degrees, and again the second one has to be 90, otherwise we're not talking about this special case. And little omega is only 10 degrees. Well, this is equivalent to doing saying big omega 20, I 90, and little omega 0. Is the difference of the two that matters. You're doing 30 degrees this way, right? Then you go down 90. And then you're doing at 10 degrees, it's equivalent to having done 20 here, 90, nothing at the end. It's the same. All right, everyone. Let's fix this eraser 3-to-1 issue. So if we do a 3-to-1 all at angles rotation, let me see if I am filming the right spot. So we said that, for example, if the first and last angle are the same, so say that big omega is 90 degrees, and the second one is also 90 degrees, and the third one is 90 degrees, this is the same as doing nothing on the first, 90 on the second, and nothing on the last one. Again, they cancel each other. So, x is pointing at you, z is up, y is this way. If we go z90, which is, it's a 3-to-1, so first rotation about the z-axis. Now x is pointing this way, y is pointing at me, z is still up, the new z, the second rotation is about the, in this case, the new y-axis, and then the x-axis is pointing down. Since it's pointing down, the 90-degree rotation of the last one brings me in this configuration, which I'm claiming is the same as not rotating about the first axis, doing 90 degrees on the second, not rotating about the last one. And that's true because I restart from this configuration, x at u, y is this way, z is up. If I only do 0 about the vertical axis, and 90 about the second one, and nothing about the new x-axis, here I am again. So this is one example where I have different combinations of big omega and little omega, first and last rotation, that give me the same orientation. That is a singularity, because again, it's not unique. So that, sorry about the confusion in class. I had to visualize it with one particular combination of angles that was making sense. And one last comment about orbital parameters. If you want, you can see things this way with the 3-1-3 sequence. Imagine that your orbit initially sits aligned with the ECI, right? This would be the ECI coordinate system. And you have H that is pointing like Z, and E that is pointing like X. Well, with the first rotation, the big omega, you identify the line of nodes, right? Going from E. So it's like saying that you're moving E here, but it's not going to stay there. So this is the big omega, and the big omega here. So that gives you the line of nodes. Then the second rotation, I, is going to give you the actual real location of H in space, and it's not going to change. And then the last rotation, the little omega, is going to, so this is big omega here, the ran, and this is y second, and this is y third, that I get, hold on, well, y prime and y second. Yes, y prime and y second. This I get it from the I, from the rotation about the line of nodes. And so the last rotation is going to occur in the plane of y second and E, well, and the line of nodes, and is going to give me the actual final location of E. And that basically fixes everything. So now we have, with 3 rotations, created, oriented correctly the line of nodes, the angular momentum, and the eccentricity vector. And I hope this clarifies a little bit more. Thank you.
We don't want to have it set up to where our first rotation cancels out the second rotation.
But that always happens if the second one does this in this case, or 0 in the other case.
Right, so are we supposed to avoid a scenario where our second rotation is 90 degrees?
Yes, what happens, so if you use a certain sequence, let me, I'll think hard about this eraser and I'll do it again. So while I do that, you choose for an aircraft, for example, you need to choose a sequence of other angles where you know that your second rotation is never going to be 90 degrees. Say that my second axis is, it's the roll axis, the direction of flight. Usually for a commercial airliner, you don't expect the aircraft to go 90 degrees. You hope it never happens, right? And so if you know that your system is not going to approach a singularity condition, say that you're doing 3-to-1, you know that your object, the aircraft, is not going to be any close, in principle, to 90, you're fine. For a spacecraft where things don't work the same, you can actually go around 360 on all axes, in principle, and, you know, and depending on the mission, it may be okay. Well, if you want to use ordered angles, what happens is when you get close to, this case, 90 degrees, you're at 87 degrees, you switch to a different representation. There are ways to switch from a sequence 321 to 313, and singularity is gone. It's just that you're changing completely the values of the angles. The parallel I can give you, you're going from Cartesian coordinates, you're tracking a point that is moving in space, you go from Cartesian coordinates all of a sudden to cylindrical coordinates. You can do that. As long as the conversion is appropriate, you can do that. They're just numbers that you're using to represent how the object is moving, right? So that's really what happens. That is what is going on. You are representing the same orientation with two combinations of, with two any combinations of two angles, as long as in this case is, well, in that case as well, as long as the difference is the same. Let me show you MATLAB before we end the lecture without showing that, and we'll go back to this. Okay. Can you see that? Is it okay? Okay. So, for those of you who have used symbolic MATLAB, this should not be new. I'm just declaring a bunch of variables that are symbolic, meaning they don't have a numerical values. Don't have any numerical values, they just exist and you can manipulate them and do operations with them. And the result will be just a formula, a symbolic formula. So I'm defining the three matrices that we have, R1, 3, and 3 big omega and 3 little omega. The I angle is inclination, the big omega is ran, argument of perigee is the little omega. I just use the same, nomenclature that we've had so far. And the same angles, dots, are their time derivatives. And this would be omega of b with respect to A. This is the matrix that I just covered with the screen. This is the determinant of that matrix because you needed to invert it. So what I do here, I just define those three matrices, right? So if I run these, I'm not printing them out, but they are there. So this is how they will look like. Of course not. Okay, so that's your first one, the little omega one, and the big omega one. So they just remain like that. They are indicated as symbolic expressions. And you can do operations with them. So what I'm doing here is I am multiplying the inverse of those two matrices, as we have written at some point, right? And well, this simplified expression sometimes makes things look a little better. Now this prime basis is what? This is that matrix that goes in front of the x third, y third, z third, right? And so each row of these is telling you how the, the x prime, y prime, z prime project into x third, y third, and z third. And so I do need, as you recall, only these two, which means first and last of the rows of this matrix. And by the way, this is posted. I posted this, you should be able to run it, assuming you all have symbolic toolbox, which I think you do. Now this expression here is putting together that omega, right there. So let's start from the last one, little omega dot z third. So now, how does z third project on x third, y third, and z third? 0, 0, 1, right? You see that? So that's why I have that piece for the last addendum of omega. So that's what it is. The one in the middle is this one, is I dot, so inclination dot, times that prime basis, I'm only taking the first row because this is x prime, and then the one in front is ran dot, is the big omega dot, times the third column of this. Okay? And so I put it together. Just do that same operation that you have on the board. I just do it symbolically in MATLAB, and then I simplify it because I like to simplify things. And I'm actually printing these out. So this is how the omega looks like. First is its projection on x third. Second is projection on y third. And third is projection on z third. So that's your omega in the basis fixed in B, the last one. And what I have done to put together the matrix I gave you is I have looked at this and reorganized it in such a way that big omega dot, y dot, I'm sorry, I dot and little omega dot are a vector. And I have a matrix in front of that, which is this one here. Okay? Now say that you need to do the opposite of what we have done. So we found this expression, omega b with respect to A is this big, I don't know how to call it, this matrix here, this, what did I call it, matrix. Okay, this thing. This is a matrix that is multiplying my vector of time derivatives of angles. And say that you want to invert this, you need to invert that matrix. And the process of inverting, I'm actually doing it there, but rather than looking at the entire inverted matrix, you can just look at the determinant of that. I mean, you can look at this, which is the inversion of that matrix, or just directly this. The end of the story is that there is this sign of the inclination, the second angle, that is dividing everything. Or the determinant of that matrix is sine of the inclination, minus sine of the inclination. And when you invert a matrix, you divide whatever you're doing on top by the determinant, if you recall. And so if that angle is 0 or pi, you cannot do it. So this relationship falls apart. You can't really relate the rates of the angles, of the ordered angles, to the angular velocity, because you can't invert that matrix. So mathematically speaking, that is the reason, another reason for avoiding, in this case, the 90-degree case. I'm sorry, the 0-degree case. This is a 313. Of course, if you do it in MATLAB, if you're running a simulation, you're actually integrating these equations, it's never going to probably give you a problem because it will never find exactly sine of 0. So we'll keep going. But again, this is another reason for avoiding singularities, because in principle, you can't invert that matrix.